Okay, let's take this one step further with a reaction that has more than one reactant. All right, so when this question asks, when it says write the rate law for the reaction, what it's looking for is this equation with the value in units of the specific rate constant K, and it also wants the order of this reactant A, and it also wants the order of this reactant B. We're going to differentiate them with two different exponents. Okay, so what does the initial concentration of A do to the rate? What does the initial concentration of B do to the rate? So let's do this first. Let's find the order of each of these reactants in turn. So let's find the order of reactant A. What we're going to do is we're going to look for a couple of experiments that change the concentration of A and don't change the concentration of B. So for example, experiments 1 and 3, we notice that the concentration of A changes, but the concentration of B doesn't. And what that means is that any effect on the rate of this reaction is only going to be due to whatever we did to A. So here's how we're going to do this. We're going to pick two experiments, and as we've already deduced, 3 and 1 are the ones that change A and not B. And I'm going to put experiment 3 on the top. We know that it has a rate, experiment 3, of 7.2 times 10 to the minus 7th moles per liter per second. This is equal to some rate that we don't know. We know that the concentration of A in experiment 3 was 3.6 moles per liter, raised to some exponent that we don't know. We also know that the concentration of B in experiment 3 is 2.4 moles per liter, raised to some exponent that we don't know. We're going to compare this to experiment 1. As we've deduced, 3 and 1 are the only experiments that change the concentration of A and not B. Well, in experiment 1, we have a rate of 8 times 10 to the negative 8 moles over liter second. This is equal to some rate constant we don't know. And the concentration of A in experiment 1 initially is 1.2 moles per liter, raised to some exponent we don't know. And B is 2.4 moles per liter, raised to some exponent we don't know. Here's what we're going to do. Just like we did this in the example from the previous example where we just had one reactant, we're going to treat these like a proportion. We're going to get rid of everything that is the same. We know that rate constant K is a constant. We can get rid of it. And we know that the value for B and its exponent are the same. So we can get rid of that too. So now what we have is this. 7.2 times 10 to the minus 7th moles over liter seconds equals 3.6 moles per liter raised to the n. 8 times 10 to the negative 8 moles over liter seconds is equal to 1.2 moles per liter raised to the n. Let's bust out our calculator. What we're going to say is, and I'm going to move this over so it's not blocking my data. We'll say 7.2 times 10 to the negative 7th divided by 8 times 10 to the negative 8. This is 9. I don't think you need a calculator for this, but if you do, here is 3.6 divided by 1.2, and that is 3. So if 9 is equal to 3 to the n has to equal 2. All right, so now you know the value of n. Let's do the same thing, and to show you that I'm being extra fancy, we're going to change colors to find the order of b. Find the order of b. And what I'm going to do is I'm going to paste this reaction in here again so I don't have to keep looking at it. All right, we're going to pick 2 experiments. This time we're trying to find b. And so we want to find an experiment that changes b and leaves a the same. Well, you can see that in experiments 1 and 2, a stays the same, but b changes. So we're going to pick experiments 1 and 2. I typically put the one that is higher on the top. So we'll say experiment 1. We know that the rate of experiment 1 is 8 times 10 to the negative 8. And this is equal to some rate constant K that we don't know yet. We know that the concentration of A in experiment 1 is 1.2 moles per liter. And we already know the value of N is 2. We're going to multiply this by the concentration of B, which is raised to some exponent m, that we don't know. In experiment 2, we have a rate of 4 times 10 to the negative 8. This is equal to a rate constant K that we don't know yet. The concentration of A is 1.2 moles per liter raised to the power of 2. And in experiment 2, the concentration of B is now 1.2 moles per liter raised to the m. All right, we're going to treat these like an equation, and we're going to get rid of everything that is the same. That leaves us with this, 8 times 10 to the negative 8. We should keep the units in there, but it's not really important now. It's moles per liter per second. I should have left them up there. Doesn't matter now, but is equal to 2.4 moles per liter raised to the m. And in experiment 2, 4 times 10 to the negative 8 moles per liter second. I should have left the units in there, but it's okay. It's equal to 1.2 moles per liter raised to the m. Now, I don't know if you guys need a calculator for this one. I'll do it with one just to be sure. But here is 8 times 10 to the negative 8 divided by 4 times 10 to the negative 8. That is 2. I don't know if you guys need a calculator for this one, but I'm going to assume that you don't. 2.4. Now I'll do it anyway. 2.4 divided by 1.2 is also 2. So that means that whatever m is, m raised, or 2 raised to the m power is 2. That means m has to be equal to 1. And that means that you now know the order for both of these. So that means that the rate for this equation is going to be equal to some rate constant K times the initial concentration of A raised to the second power times the concentration of B raised to the first, which we don't even need. So now what we want to do is find the value and units for the rate constant K. Let's start that over because that was going to look sloppy. What we're going to do is we're going to pick an experiment. And we're just going to plug everything in and find the value and units of the rate constant K. I'm going to I'll plug this back in down here so we have it. Let's pick experiment 1. Okay, so we know that for experiment 1, let's make sure we're talking about experiment 1, we have a rate of 8 times 10 to the negative 8 moles per liter per second. This is equal to some rate constant K that we don't know, but we also know that the value of A in experiment 1 is 1.2 moles per liter squared times B, which is 2.4 moles per liter raised to the first power. I want to solve for K. So to do that, I'm going to express everything over on the right of the equation so I can start to get rid of it. So now we're going to take 1.2 and we're going to square it and its units. 1.2. Whoops. 1.2. I don't think that's going to work. Screwed it up. 1.2 squared is 1.44. So now we have 1.44 and we're squaring the units as well. Moles squared over liters squared. And we're going to do the same thing with this. This is now 2.4 moles liters. Nothing happens. Let's multiply both of these together. So now we have 8 times 10 to the negative 8 moles over liter seconds. You see with a K, which we don't know, I'm going to take everything in here and multiply these two together. Moles squared times moles is going to give us moles cubed. Liters squared times liters is going to give us liters cubed. All we need is the value 1.44 times 2.4. This is 3.456. Let's call that 3.46. All right. We want to solve for K, and we're going to get its units. 8 times 10 to the 8 moles over liter seconds divided by 3.46 moles cubed over liters cubed equals K. So the value for K is going to be 8 times 10 to the negative 8 divided by 3.456. We rounded out to 3.46. 2.31 times 10 to the negative 8. And what happens to our units? Moles on the top cancels one of these moles on the bottom and leaves it moles cubed. Liters cancels one of the moles squared, liters on the top cancels one of these, leaving it liters squared, and seconds stays the same. So now what we have is moles squared in the denominator over liters squared in the denominator, and that flips them over. So the units are liters squared over moles squared times seconds. And that's all you do. There's lots of ways that you could rewrite these units. Your textbook is going to say this. It's going to say 2.31 times 10 to the negative 8 liters squared over moles squared is the same as the inverse of molarity, and so it's going to write it as molarity to the negative 2 times seconds to the negative 1. So this is the square of the inverse, and this is just the inverse. This unit, I actually like this better. Okay, but you can write it however you want.